Okay, so we're back with the fourth video on derivation of the micromechanical properties of a representative volume element. Now I included a small drawing rather than my sketch. So we are assuming one layer, a lamina, where we have fibers embedded in a matrix. All the fibers are straight and parallel to each other, and both the matrix and the fiber are linear elastic, and the constituents of these two are also, of course, isotropic. We assume displacement continuity and force equilibrium as previous. So we can take that away now. And so let's consider this small representative volume element where we have a matrix, fiber matrix. So fiber embedded in matrix. If we now apply a force in this direction, the system will deform like this. So we will have a stretch, a deformation in, I'll change the color to blue instead. So we will have a deformation here, which is then delta 1, and we will have a deformation delta 2 as an effect of the Poisson ratio. So when we stretch the material in this direction, in one direction, it will deform in two directions, like that. So by definition, the Poisson ratio, ny12, is the strain in two directions divided by strain in one direction and the minus sign. This is the definition. This is the definition we're using for Poisson ratio. Okay, so what is delta 2 here then? Well, that is of course the thickness of the system times the strain in that system. So we have a original thickness here, which we denote as h, like that. So the deformation in two direction, the shrinkage, how to say, total deformation in this direction is the thickness times the strain in two direction. But it's also then, by plugging this in, we denote that as the Poisson ratio 1 to times the strain in one direction, so strain in this direction. Right. This deformation delta 2 is of course the deformation of the matrix and of that of the fiber. So it's the deformation to F plus deformation to M. Right. So using this, we plug this into, because that is of course the same for the fibers and the matrix, so this is a general. So we can plug this in, so that is the thickness of the fiber times the Poisson ratio for the fiber and times the strain in the fiber in one direction plus the thickness of the matrix times the Poisson ratio 1, 2 for the matrix times the strain in the matrix in one direction, like that. Okay, so we know from previous that we can convert this thickness or h into volume fraction. So for example, h over f, or hf over h, that should be an h, is the volume fraction of the fiber. And of course the same goes for the matrix, so that is the volume fraction of the matrix. So I'll try to distinguish or write clearly so you can see the difference between the Poisson ratio and the volume fraction. So the deformation in 2 is the total thickness times the Poisson ratio 1:2 times the strain in 1, like that. Using this, we can now write the Poisson ratio 1:2 times the strain in 1 equals, so that's coming from that. Sorry, I forgot, actually this is going to be a negative sign in front of here. Sorry for that. We can now, delta 2 is this expression, so we move that down here, and then we can put this in here as well. So we then have the volume fraction, remember this, times the Poisson ratio, the fiber, times the strain in the fiber in one direction, plus the volume fraction matrix times the Poisson ratio for the matrix times the elastic modulus in one direction. But remember from the derivation of E1, if we deform this volume element like this, we assume that this line is perfectly parallel to the original shape, meaning that the strain in the matrix and the fibers are the same. So these terms are equal, so hence they disappear. So the Poisson ratio for this system is the volume fraction of the fiber times the Poisson ratio of the fiber plus the volume fraction of the matrix times the Poisson ratio of the matrix. And as we see, this is a linear function, so if we try to plot the Poisson ratio for the system as function of the volume fraction for the fiber, so here we have 100% fiber, so up here is the Poisson ratio for the fiber, and here is the Poisson ratio for the matrix, and that is a linear function like that. Okay, thank you.